All right, my fine young chemists, welcome to our next unit, Unit 3 in the IB curriculum, which is all about periodicity or periodic trends. And so we're going to try to get a lot of the basics out of the way in this first video. A lot of definitions coming your way and a lot of explanation for the periodic trends. And we're going to get this stuff going and done so that we can get on to chemical reactions and look at a lot of the more interesting stuff. So this part where we're going to talk about periodic trends, I would say is 95% a review of last year, and that's pretty awesome for you guys. What are the periodic trends that we will be covering? Well, we have to know what happens to atomic radius. That means the size of the atoms. Do they get bigger, smaller? What happens as you go across the periodic table and as you go down? We're going to look at ionization energy. Okay, so that one, ionization energy, we've already covered, and you should be pretty familiar with that. We are going to look at electron affinity. Okay, we'll define that here in a little bit. We are going to look at electronegativity. These two, many students get backwards, so we're going to have to be careful with that. Those first four right there are the main ones, and the last one we are going to look at is ionic radius. That's fine. Now there's one more besides ionic radius that the book calls for in this chapter, which is melting point. And we're not going to cover melting point now. We're going to wait until the end of chapter 4. So any problem you see that has a melting point question, don't sweat it. You'll find them in the homework. So if you see one, just kind of be like, oh, okay, Crawford will cover that next unit. Let's let it go. Don't sweat it. And of course, I would not put melting point on any kind of assessments for this unit. Okay, so these 5 periodic trends are the ones you need. And the reason I drew a line under that, these all follow the same pattern. This one's just a little bit different. You'll see that here in just a second. Okay, so before we get too far down the road, we need to make some definitions. This is a really funny one. The definition of periodicity. It's really weird that it's not in your book. Your book doesn't define periodicity. The IB doesn't define periodicity in the curriculum, and yet that's what the whole dang chapter's about. So we probably ought to define that for us. What does it mean when we have a periodic table, quote unquote? What does period for the periodic table mean? So here you go. It's the repeating patterns. The repeating patterns. This is both chemical and physical. Okay. Of the elements as atomic number increases. Again, you can stop the video and write that down, but so periodicity, there is a repeating pattern that the elements undergo as you go through the periodic table. So periodicity is all about this repeating pattern that we're going to see over and over and over again, whether that's in a family and so on. So that's what we're actually talking about from a periodicity is, what are those patterns that happen? All right, so that's your first definition. I don't think it's an IB def, but gosh, it kind of would be important to actually talk about that, given that that's the whole chapter. Okay, next definition, one that you definitely need to know, and you already know this, is nuclear charge. So the nuclear charge is the number of protons. Number of protons in the nucleus. Yeah, that's the charge, the nuclear charge, the charge on the nucleus. And since the nucleus only has protons and neutrons are neutral, then the nuclear charge comes from the protons. Okay, not rocket surgery. So that one's pretty simple. I'll define two more here, and then we'll work with them here in just a second. Next comes shielding. And I heard many of you talk about shielding in our last unit. I heard some misconceptions, so let's define it carefully. Shielding is the blocking of the attractive force of the nucleus by the inner or core electrons. And I'll draw this out for you here in a second, and we'll talk about it, and I think you guys are fine with this. So the inner core, or the electrons not in the valence shell, they block the attractive force of the nucleus as it pulls on the valence electron. So it's the blocking of the attractive force of the nucleus by the inner core electrons. Okay, great. And now comes the biggie. ENC stands for effective nuclear charge. And this is the one, okay, critically important. I'm going to underline it here in red. Effective nuclear charge is the definition you are going to use when you explain these periodic trends up here. So we have to define effective nuclear charge, and I'll write it out for you. I'll show you the equation that we're going to use, and we'll work a couple examples. So effective nuclear charge is the pull of the nucleus that a valence shell electron feels. So I'll put it here. The pull of the nucleus that a valence shell electron feels or is pulled with. And it's actually a calculation, and it's really simple to do. It's the number of protons in the nucleus minus the number of core or shielding electrons. Really, really simple. So protons in the nucleus, you just look it up for an atom, and how many core electrons. And we kind of got that. So let's kind of do a simple calculation, if we would, and if we can. Let's see, just grabbing periodic table. So let's start and let's calculate effective nuclear charge for sodium. Sodium is element number 11. So here we go. Here's sodium, and I'm going to draw, here's its nucleus. The nucleus of sodium has 11 protons in the nucleus. Now, what is its electron configuration? It's 1s2, 2s2, 2p6 going up from the nucleus, right? This is going up in energy. You don't have to do this, but it's just the way that I like to represent it. So it's 1s2, 2s2, 2p6, and then sodium is 3s1. Cool. Okay, so how many protons does it have? Number of protons, right here, 11. How many core electrons does it have? It has these. These are your core, right? Not the valence shell, everything except the valence shell. So how many are there? 2 plus 2 plus 6 makes 10. So there are 10 core electrons here on this guy. So how are we going to calculate the effective nuclear charge? It's the number of protons minus the core electrons. So we have 11 protons minus 10 core. The effective nuclear charge is 1. What does that mean? There are 11 protons pulling on this outer valence shell, but 10 out of the 11 protons are shielded by the core. In other words, if you even want to think of it as canceled, they're not really canceled, but these core electrons reduce the field that this electron gets from the proton, and it's reduced by 10. So 11 protons reduced by 10, the shielding is 10, gives us 1. And that's for sodium. Let's go to the next element over, magnesium. Magnesium has 12 protons. How do I know? It's element number 12. Now the core electrons are going to be the same. It's 1s2, 2s2, 2p6. That's all the same. It's only the valence shell electrons that have changed. We have one more electron in the valence shell. So how are we going to calculate effective nuclear charge? It's 12 protons minus the 10. Where are 10? Well, the core electrons are the same. So no difference in the core. So the shielding is the same while the number of protons goes up. 12 minus 10 is 2. That means these outer valence electrons here are feeling the pull of 2 from the nucleus. Effective nuclear charge has gone from 1 to 2. We can do one more. Aluminium, if you wish. It's element number 13, so it has 13 protons. Its core electrons are the same, 1s2, 2s2, 2p6. It still has 10 core electrons. It adds another electron to the valence shell, 3s2, 3p1, but the core electrons are the same. So how would we calculate effective nuclear charge for this guy? 13 is the number of protons. The core electrons are 10. We subtract those and we get 3. So what is actually happening as we're going across this period 3 of the periodic table? The effective nuclear charge is growing. It's going from 1 to 2 to 3. And as we go across, the outer valence electrons are feeling a greater and greater pull of the nucleus. Okay, so we don't just say, oh, they feel 11 or 12 or 13. We have to account for the shielding. So there we go. Effective nuclear charge has a calculation, and that's what you're going to want to use when you're describing a periodic trend, is we want to use that effective nuclear charge value as we kind of make our decisions about what's going to be happening in terms of periodic trends. Okay, so we've got those. Now, periodic trends. I'm going to get a nice clean sheet of paper here for you guys. Okay, remember those 4 periodic trends that I wrote first? Atomic radius, ionization energy, electron affinity, and electronegativity. We need to define those 4 terms. And so let's do that now. Atomic radius, that's literally the radius of an atom. Now, we've got a problem with that, in that if you were to take an atom, and here's the nucleus, and where, if you want to say, oh, this is the radius from here to here, an atom isn't a circle. An atom has electrons in its valence shell, which live in orbitals, and those orbitals are the probability of where that electron is 90% of the time. This is a hard thing to measure if you just took an atom and said, oh, let's figure out the radius. That's because this boundary is getting, that the atomic radius, if the electrons are on the outside, it looks a little bigger than if the electrons have gone inside those orbitals a little bit. Then you might say, oh, it's smaller, then it's bigger and smaller. So how do you measure that? Is it getting bigger or smaller? So the way we actually do that is we bond that atom to another atom. And let's say this is a hydrogen bonded to a hydrogen, so we have H2. we take the distance between the two nuclei, we take that total distance and divide it by 2. And that gives us the radius of one hydrogen atom. Now, you might ask, well, how do we know the distance between two hydrogens? That can be figured out using X-ray crystallography. Did I spell crystallography right? Probably not. There's no H. Excuse me. Crystallography. And X-ray crystallography is a technique by which you bombard a solid sample, a frozen sample, and look at the X-ray diffraction pattern that comes from that, and you can determine the distance between two nuclei. Okay, so that's atomic radius, and you'll see different units, but of course it's a distance, so it's measured in meters. You'll see smaller things, smaller units of meters, that like picometers and stuff, but it's still a meter. It's still a distance. Okay, so we've got atomic radius worked out. Ionization energy. I'm not going to give you the definition written down. Let's make this video short, but you had it for the last unit. The amount of energy required to remove 1 mole of electrons from 1 mole of an atom in the gas phase. Okay, so that's ionization energy. To remember, with ionization energy, we're trying to take the electron away. We're trying to take it from the ground state, wherever that is, and remove it off of the atom. Now, we talked about this as a transaction, right? So if you want to take an electron away from an atom, you have to pay for it. So if you're taking the electron away, you've got to give the atom something in return. And what are you going to give it? You're going to give it energy. So when we say ionization energy, we're really talking about the amount of energy in kilojoules per mole that you have to give the atom to take an electron away. Right? Think of it as a transaction. You're paying the atom for the electron. Now, something that is exactly the opposite is electron affinity. It is the exact opposite of ionization energy. In electron affinity, the atom wants to, and let's be careful about wants, it doesn't want anything, but we use that term. The atom would prefer to take an electron. So it's like, oh, I'm going to buy that electron. So electron affinity is how much energy the atom is willing to give up to gain an electron. Okay, so these two, ionization energy and electron affinity, are opposites of each other. Again, ionization energy is how much energy you have to give an atom to take its electron. Electron affinity is how much energy the atom will give you in order to gain your electron. They're the exact opposites. Now, ionization energy is critical. Ionization energy is what we are going to use for metals. We know that metals give up electrons. That's what makes them metals. That's why they are on this side of the periodic table. All of these elements prefer to give up an electron by gaining energy in its place. Nonmetals, of course, are the opposite. Nonmetals want to gain electrons to form a noble gas. So when we're talking about electron affinity, we are talking about this for nonmetals. How much energy does a nonmetal give up in order to gain an electron to form the noble gas configuration above it in the periodic table? That's electron affinity. Okay. Last one here is electronegativity. And electronegativity, we're going to talk more about in the next unit. Electronegativity is, let's put a nitrogen bonded to an oxygen. So remember, those two electrons represent the covalent bond between nitrogen and oxygen. Electronegativity is the ability of an atom in a covalent bond to pull the bonding electrons towards itself. So here's two electrons shared. Which one of these two elements, nitrogen or oxygen, could pull those electrons more towards itself? And in this case, we're going to say it's oxygen. And so those electrons are pulled this direction towards the oxygen. Don't worry about the symbol. We'll talk about the symbol a little bit later. Okay, so 4 of these trends that we're going to be talking about as we go across the periodic table, right? So now what we've got to do is figure out, how do those 4 trends vary? Easy peasy, I hope. This rectangle represents the periodic table. Okay, I know it's not a very good one, but you have to be able to talk about the trends going across the periodic table and the trend going down the periodic table. Let's talk about this for atomic radius. What happens to the size of an atom as you go across the periodic table from sodium to magnesium? Well, the argument you're going to make when you're going across the periodic table is always going to be an argument about effective nuclear charge. Okay, so what's actually happening with effective nuclear charge? The number of protons is going up, the shielding stays the same, so the effective nuclear charge grows. What does that do to the atom? Atomic radius gets smaller. Okay, now what about going down? The argument you will always make about periodic trends going down is all about energy levels. So as you go down, the electrons are being added to an energy level further from the nucleus, so atomic radius gets larger or increasing. Okay? I'm going to just represent it this way. Every time you talk about the periodic trends for atomic radius, ionization energy, electron affinity, and electronegativity, your argument will always be an effective nuclear charge argument going across. It will always be an energy level argument going down. Always. Okay, so here's another periodic table. Let's talk about ionization energy. What happens to the amount of energy you have to give an atom to take its electron away? Well, as you go across, effective nuclear charge goes up, the number of protons goes up, there's a greater pull on the valence electrons, ionization energy increases as you go across. It gets harder and harder and harder to take the electron. How about going down? Again, that argument will always be about energy levels. The electrons in the valence shell are in an energy level further from the nucleus. Electrostatic attraction decreases, and so it's easier and easier to remove them. So ionization energy decreases. Okay. Notice the trends are always opposite. So if one of them gets smaller, the other gets larger. If one of them gets larger, the other gets smaller. Okay. How about the amount of energy an atom will give you to take an electron away? That is electron affinity. Okay, as you're going across, you remember you're going from metals to nonmetals. Nonmetals really want to gain an electron more and more and more and more, so they'll give more and more and more energy to take them. That's because there are more protons with the same shielding, so electron affinity increases. As you're going across, the elements are becoming more and more desirous of taking an electron. As you go down, it's all about energy levels. The electrons are further and further and further from the nucleus. So once it gets out really far to the outer shells, the nucleus is like, I'm not going to give you any energy for that electron. Forget it. You're going into an orbital too far away for me to care about. So this decreases. And the last one. Okay, so the last one, we've got atomic radius, ionization energy, electron affinity, and electronegativity. Remember that these, I'll remind you over and over, these are not the same. This is, electron affinity is in kilojoules per mole. It's the energy an electron, an atom will give up to take an electron. Electronegativity, on the other hand, is the pulling of the electrons in a bond towards itself. That said, the trend is exactly the same. Electronegativity increases, and as you go down, because of the energy levels, this decreases. Okay, remember your arguments going across are always about effective nuclear charge. Your arguments going down are always going to be about energy levels. Okay, I'm going to turn this off here and kind of shut this video down. We're already at 26 minutes, which is a long video. I think that's actually my record. I was trying to fit this all into one. We're going to come back and talk about ionization and the radius of an ion. We will do that later, but these are the 4 biggies that you guys need to know. Okay? All right, guys, I will see you next time. Thanks for being here.